Ladies and gentlemen, welcome for all. In our present lecture, we will discuss an advanced procedure for design and sizing of a grid solar photovoltaic system using manual calculations and simulation. Also, we will discuss a case study of 4.5 kilowatt as peak power. Okay. Our learning objectives of this series of lectures will be as upon the completion of this series of individual lectures, we should be able to make a complete design for any of a grid solar photovoltaic home system, as we see in this scheme, the scheme of an off-grid solar photovoltaic system. And I would like to introduce myself. I am Samah Ode. I am a lecturer in the field of solar and wind energy. I am BSc Mechanical Engineering, MSc Project Management, specialized in the field of wind energy, and I have certified by RENAC Academy and Solar Energy International from USA and other websites that specialized in the field of solar energy. I am here because I would like to give for all as a series of lectures corresponding to the design and sizing of 4.5 kilowatt as peak power and of a grid solar photovoltaic system, and also give you the basic for starting the design. Also, we will discuss the manual calculation by using mathematical equations and showing how the results are matching with the results of simulation as using PV-Sys 7.2 and another software, PV-Sol, and SketchUp software packages. Okay. In the first lecture, we will constrain our attention will give up about the geographic location of photovoltaic installation, and we will also discuss the solar radiation concept and methodology of design calculation for solar photovoltaic system, and also we will take some details about design consideration for solar photovoltaic system. In the second lecture, we will discuss inverter sizing, or we can say how the ratio of array of photovoltaic to inverter sizing factor. And also we'll discuss why oversizing the photovoltaic array with respect to inverter. And also we'll discuss the clipping losses and DC to AC ratio. And we will discuss what happens when oversizing inverter, AC capacity, or when DC to AC is less than 1. And also we will discuss photovoltaic cost with and its relation with the DC to AC. Okay, in the third lecture, we will discuss design steps of solar photovoltaic system, which include the following steps: loading size, battery bank capacity sizing, inverter sizing, solar array sizing, and we also discuss if there are any differences between the results of manual calculation and the results of simulation, and we will discuss if there is any differences between the results of two procedures. In the fourth lectures, we will discuss and talking about the other component of the system, which is already called the balance of system, as installation structure, contactors, fuses, grounding or earthing, monitoring instruments, etc. Also, we will discuss the area required for installation of a photovoltaic system, and shade analysis, shading losses, orientations, and tilt angle that's required for photovoltaic modules. And also, we'll make a calculation for cable sizing. In the fifth lectures, we will discuss the installation steps of a great solar photovoltaic system. And also when we required another or the sixth lectures, this will be depend upon what additional information we must add it for this series of lectures. Okay. Now for the first section of the first lectures, we will discuss the geographication of photovoltaic installation. If we consider the given known data for our system and represent as given data for the system capacity 4.5 kilowatt peak power as of grid solar home system, the place that we intended to install as arbitrary location in Baghdad with the coordinates 33.15. This is the latitude, and longitude 44 degree. As we see this map of installation, or which represent the geographic location of photovoltaic installation at the southern of Baghdad. Okay. Now we will discuss some notes about the solar radiation concept for the selected site. In general, solar radiation for selected site, the solar radiation component, as we know, there are many components for the solar radiation. The main component represents the direct normal radiation with the simple DNI, and also the second component, diffuse horizontal radiation, DHI, and the summation represents the global horizontal radiation, GHI, and the global tilted radiation, GTI, which represents the total radiation over the tilted surface of photovoltaic system. And also we have another component which represents the albedo. Albedo is the present ratio of what surface of the air reflects directly to space from the incoming pure solar radiation on the ground. As we see in this diagram, this represents the global horizontal and global inclined solar radiation for the selected site at Baghdad. As we see from this diagram or this component, this represents the global horizontal radiation, and this is the sum 1818 kilowatt hour per meter square, and the light lines diagram represent the global incident solar radiation collector plane. As we see, the total global solar radiation on inclined surface seems more than the global solar radiation on horizontal surface. This is why we can discuss why the average of total or global solar radiation or inclined on inclined surfaces more than the global solar radiation on horizontal of the earth or the ground, because the inclined surfaces represent the solar radiation on inclined surfaces always represent or coming from three components which represent direct solar radiation, diffuse solar radiation, and reflected solar radiation. And the global solar radiation on horizontal surfaces always taking into consideration two components only, which represent the direct solar radiation and diffuse solar radiation, and sometimes neglecting the reflected solar radiation. Okay. Now, if we taking a little notes about this table of metallurgical synthetically generated data from monthly values, this table was generated from the environmental condition for the selected site for each month through the year. As we see, the interval beginning and the second column represent the global horizontal irradiation. This represents the monthly value measured by kilowatt hour per meter squared per month, and diffuse horizontal irradiation, also these values. And the fourth column of the table represent the beam horizontal irradiation and monthly values, and this also represent beam normal also, as we see, and this column represents the global solar irradiation on tilted surface, as we see, more than horizontal, global horizontal, and also taking into consideration the ambient temperature, the average daily for every month through the year, and also taking into consideration the wind level measured in meter per second. Okay. Now we will talk about the sizing strategy or the methodology of design solar photovoltaic system. If we take a little looking for this diagram, we will see that there is two arrows starting from solar array and ending with loads. This represents the energy flow, the energy generated from solar array via the charge controller, then into the battery bank, and converting from DC to AC by the inverter, and then for operation of the appliances or the load in the home. Now, after we know the flow path for energy, now if we would like to make sizing for the system, we shall start from the load. So the sizing strategy is an opposite direction for energy flow. When we want to calculate the system size, we will, as we will see in the next lecture, we will start from the evaluation of the appliances in the home, and we take into consideration every appliances and the number of appliances, the wattage or the power of every appliances, number of operation of during the day, and then after that we will take the summation of total energy required for the load in order to take the result of our calculation for energy required for operation to calculate every component of the system. So we conclude that the energy flow is an opposite direction for calculation procedure. Okay. Now, there are many points or consideration for off-grid solar photovoltaic system design. Now, we will discuss the first consideration. We must select the appropriate type of photovoltaic system to be designed. As we see from these pictures or figures, you either construct your small system on ground, as we see, or on tilted roof, the second one, or on flat roof, or as a small for a small roof or big roof. As we see, this structures built on the roof of the buildings. Also, as we know, we have two types of systems, either off-grid system or on-grid system. So we must select the appropriate type, and what we know about the component of the system, and what we want to design, small system or large system, and the place we want to install that system, or maybe our system consists of photovoltaic system and other energy source such as wind turbine as a hybrid system. The second issue, we must determine the type of loads to be fed. As we know, there are two types of loads, either DC loads, as we see for this scheme, the loads, lighting, or for phones or small phones of small loads, of course, TV, DVD, for charging the phones, and DC lighting. Another type, we have AC load, as we see in this diagram. The energy coming from the solar and entering the battery bank through the charge controller, then convert the energy from DC to AC to feed the AC load. Or we have a combination of both DC and AC load. As we see, we have in this diagram, we have AC loads, and also we have DC load that can feed directly from the charge controller. Another issue we must take in our consideration, the appliances operation hours required that must be fed from the photovoltaic system and battery bank. As we see, and we know that energy coming from the solar's energy and stored in the battery bank in order to use in the time where the sun is absent during the night, and we must take into consideration the size of battery bank, and this will be discussed in the next lectures, and how we can sizing the battery bank, the number of batteries, the way of connections, how many batteries in series, how many strings of batteries. So we must take into consideration the number of hours that the stored energy in the battery can be feed the loads from via the inverter in order to operate the AC loads. Also, we see in this diagram the photovoltaic system and solar battery chargers, and energy will stored in the battery, then during the battery charging, and during the night we will take the stored energy from the battery in order to feed the electrical load. This will be discussed as I say in the next lecture, and we must concentrate on the stored energy in the battery. As we see this scheme showing that inactive or stored energy in the green color, and this represents the discharging energy, which referred as empty, and the total line represents the rated capacity of the battery, and from the bottom end of the green zone to the top of the battery represents the available capacity that can be used, which represents the depth of discharge for the energy that can be drawn from the battery bank. And this represents the state of charging for the energy stored in the battery. Okay. Also, another consideration or energy consumed by the load. As we know, in every home, every household, there is a number of appliances such as a refrigerator, TV, fluorescent light, fans, DVD, and other, and so on. How many appliances in the home, and the numbers of units for each appliances, and the power of each appliances, and the total power required for these appliances, and also take into consideration the maximum power consumption, and then we will calculate the average power consumption measuring in kilowatt hour per day in order to make our sizing of the system. If we are looking up the profile load, as we see, this represents the time for 24 hours, and this represents the power required for the appliances in order to operate these appliances. As we know that, as example for this diagram, the sun will rise at 6 o'clock and continue on their rising until to reach its maximum altitude in the sky down, and generating the energy at the noon time. This yellow or this curve represents the generation of our system, solar system, and this represents the energy consumed from the battery starting from the midnight till the 6 o'clock, as we see, and also at the evening time we will the energy required for the appliances will be drawn from the energy stored in the battery bank. In this you see, this represents the behavior of the load consumption. Now, the dark yellow, this zone, represents the household, the appliance house power by solar, or the consumption of the appliances directly from the generation energy from the solar photovoltaic system. And the excess energy represents the energy that will be used for battery bank charging. This energy will be, as we said before, will be stored in the battery bank and will be used at the times, in the evening times, or the hours during the night. So any excess energy will be stored in the battery bank, and the required energy under this curve, this blue line, represent the energy consumed by the appliances and the home. Another criteria, we must selection the inverter type and the size. There are many options for the inverter selection that can be used in off-grid system. As we see for this scheme, the solar photovoltaic panel, the charge controller, and the inverter. I would like to make a notation that this is the inverter, as we see, and this is the charge controller. Sometimes the charge controller would be coming as a separated part from the inverter. Okay, if we come here for this scheme, we see that the charge controller for charging and regulating the energy from solar photovoltaic to charge and discharge the battery. So, as we see, the inverter with controller, it means that the charge controller coming built in with the inverter. Another type, we can, as we see, sometimes we have a DC coupling system. As we see, the arrays, array 1, array 2, and the charge controller for each array, and then converting the power from the solar photovoltaic DC to also DC. This is the DC converter for the charge controller. Then the energy coming from the strings of the array will charge the battery system, and then by the battery inverter charger. This is another type that can be used in the DC coupling system, or an off-grid DC coupling system. This type battery inverter charger, which have, or we can also refer to it as a multi-mode inverter. Then the energy can be converted from DC to AC in order to switchboard or main switchboard, and then supply the appliances and the home. Also, this type of inverters, which called battery inverter charger, have the ability to receive the energy from other sources of energy, such as generator, diesel, as we see in this scheme of this diagram. Also, another consideration that we must be taken while we are doing sizing and design an off-grid system, you must take into consideration the type and capacity of solar battery. Common type of battery that pair with a residential solar system, lead acid batteries, and lead acid batteries have more than one type, as flooded lead acid batteries, or which have vented in order to release the gases from that generated through the process of charging and discharging. This is, of course, the most common type, flat plate lead acid batteries, or this type, and other type tubular lead acid batteries. Also, as we know, this is more widely used in off-grid system, and most affected. Their prices or their cost is less compared with other type, and also represent the least cost per ampere hour of any type of batteries, other type of batteries. This kind of batteries, lead acid batteries, require regular maintenance, which represent water filling and checking the specific gravity of the electrolyte chain. And this type of batteries, as I said, release the toxic hydrogen gas, so it requires vented opening in order to release the hydrogen gas in the environmental, in order to dismiss the hydrogen gas out of the space, in order to keep the home from the dangerous cause of explosion or any playing by the kids or other human, in order to keep the healthy of the family that was installed their own photovoltaic system in their home. Okay. Of course, this type of flooded lead acid battery, this is flat plate, and this is tubular type, and this represents the way of connection of the batteries and the package. Okay. Another consideration type of batteries, we have a valve-regulated lead acid, VRLA, or sometimes referred to SLA, sealed lead acid batteries. This is the best environmental temperature for VR, valve-regulated lead acid batteries. The temperature range for base operation from 20 to 25 Celsius, and the round trip efficiency for gel and AGM about from 80% to 90%. The AGM battery that represent absorbed glass mat battery represent a deep cycle absorbed glass mat used in off-grid solar power system, and can be placed in a poorly ventilated location, because there is no gases released in the process of charging, and also contain a built-in valve to release any excess gases in the event of overcharging. and also this type of batteries need fewer ventilation requirement. And the third type is the gel battery, maintenance free and fully sealed and no acid leakage, and also not release acid mist when charging and discharging. This is the more common type of batteries that used in the solar home system. This is absorbed glass made battery. As we see, the component of the battery of the AGM, and this is also represent this type of Porta battery, which represent the AGM battery, and this type represent the gel battery, also deep cycle gel battery from this company. Okay. The other type of batteries that can be used with off-grid solar photovoltaic system in deep cycle lead acid OPZV tubular gel battery. This is also contained or represent bar-regulated lead acid battery single cell, which have, as we see in this figure, the voltage for the cell 2 volts batteries linked in series to form either 24 or 48 volts. This represents German technology stationary tubular plate closed battery, and have a cycle life up to 5,000 cycles for 15 years, 20% depth of discharge, and 3,000 cycle are 40% of the depth of discharge. The temperature range for operation, base temperature range, is from 50 to 30 Celsius. Okay. Another consideration for off-grid solar photovoltaic system, we must make our selection for well-proofed type and size of solar module. As we know, there are 3 more common type of solar modules. First one, or most popular type, monocrystalline solar panels, mono SI, which represent purest type, and as we see, this type uniform dark look, and also rounded A, and their efficiency range from 18 to 24%, more energy, and require less space when installing on roof or even on ground. So it's occupy less space. It means that more space efficient. But this type is more expensive than the second type, which represent polycrystalline solar panels or solar modules. As we see, this type, monocrystalline polycrystalline silicon, angle are cut, polycrystalline silicon. The cells represent square type. The edge are not cut as compared to the monocrystalline silicon, represent low cost, and the typical efficiency range from 13 to 17%, and need more space, and even their effect with the temperature is little different with the monocrystalline modules or monocrystalline solar panels. The third type of solar modules, this is the thin film solar cells, TFSC. This type can be applied for building integrated purposes, as we see, more flexible, and their efficiency range between 7 to 14%. And technical aspects of the selected module operating, this is another issue we must take in our consideration, the operating voltage of the array, which represent the operation, the safety operation of our array at lowest and the highest temperature for the module. Always should be within the maximum power point tracking range of the inverter. In case of on-grid system, this is very important note that we must take in our consideration. We must concentrate about this expression, that the operating voltage of the array must be at the lowest and highest temperature of the modules or the string, should be within the maximum power point tracking range of the inverter in the case of on-grid system. So what's the difference with an off-grid system? This will be discussed later. So we are looking carefully for this diagram. As we see, this represents in x-axis the voltage and the current on the y-axis, and this represents the array voltage sizing in case of on-grid system. Although we are discussing the procedure for design of a grid, but I would like to remark this notation because there is a related notation in our study. So, as we see, this is the temperature 60 Celsius, and this is the lowest temperature T 20 Celsius. Okay, and the range that the inverter will that the string of modules must operate in this range in order to make the operation of the system as a stable system, and in order to protect the inverter from the high voltage in case of high voltage coming from the string, and in order to keep the running of the inverter and avoiding the event when the total voltage coming from the string became lower than the lower limit of maximum power point tracking, in order to avoid the stopping or switch off the inverter. So the second case, in the case of a grid system, the operating voltage of the array at the lowest and the highest temperature of series modules that we connected as a string should be within maximum power point tracking range and operating voltage of the solar charger. Look at this. Here we are talking about the solar charger and not course, the solar charger either will be separated or built in within the inverter. This is in the case of a grid system. If we are looking this table, this represents a series of electrical characteristics of inverters. Of course, most inverter. I already in my design choose the module PV 34 kilowatt VHM that operate on 48 volt DC, 4 kilowatt, and the surge rating. This is the rated power for kilowatt, and the surge rating for this model 12,000 volt ampere. Okay, this is the notation that I would like to remark for the solar charger. As we see, for this type, the range of the voltage from for the 48 DC system voltage, the range from 64 till 145 volt DC. So the voltage of the string must be within this range, not below the lower limit, and must not exceed the maximum limit of MPPT range. This is very, very important issue. And as we see that the maximum photovoltaic array open circuit voltage for this type also 145 volt DC. We must never exceed this value of the upper limit of MPPT range of the solar charger. This is very important notation that we must be taken in our consideration while making our calculation. Either we do our hand calculation, or we must select the suitable inverter in our simulation by using an advanced software such as PV software package. Okay. Now, other criteria must be taken into consideration: the efficiency of the modules, which represent the multiplication of the voltage at maximum power point multiplied by the maximum power point current divided by the area of the module, also and multiplied by the impedance at standard test condition. Also, we must know the value of, as we see, the current at maximum peak power, and the open circuit voltage, and also the current at the of short circuit current, and also I must know the area of the module in order to evaluate the efficiency of the module. Okay. Also, we must take into consideration the normal operating cell temperature and on CT. For the same value of normal operating cell temperature, PV module with higher rated power should be selected. If we have more than one modules in the market, and we are going to the market in order to buy or to select the solar modules, we must take our attention on every item of electrical specification. And one of these criteria of electrical consideration is the normal operating cell temperature. We must choose for the same power of more than one module, we must select the module with higher normal operating self-temperature in order to make our assurance that this module will be able to work at base condition and hotter climate condition. Okay, another type of criteria is traditional equipment and product warranty and power warranty. If we are looking about this diagram, so this represents the year of operation of modules. Of course, this type, monocrystalline silicon module from Longi company. Always we must take in our consideration the style of degradation of the module. We select the straightforward degradation better than the standard degradation. As we see, this company tell us for the first year of operation, the degradation will reach 91.2% for the first 10 years, and the other years of module life till 25 years will be 18.7%. This is very good indication when make our selection for the best module type. Also, we must take in our consideration the warranty that coming with the data sheet of the module. As we see, this type polycrystalline silicon 300 watt, and this is 25 years of warranty. This, if we look at carefully, as we see, 25-year performance warranty. Okay, this is very important issue. On 10 years working warranty. Okay, and also we must take in our consideration the certification of the module that produced from the factory or from manufacturing. As we see, the certification IEC, TUV, CE, ISO, and other type of certification. This is very important issue, and whenever we see the and we select C and selection high quality of solar modules, we can see more certification will be written in the data sheet of the base type of modules that we want to select. We must take our attention on this type of certified for the selected module. Okay. Also, there is another criteria which represents the power tolerance. The power tolerance represents deviation from the guaranteed output for design an efficient and reliable system. As we see, this is some specification from manufacturer with this Shine Solar 300 watt monocrystalline silicon. As we see, the tolerance represents from 0 to 5 watt positive power tolerance. Always we must make our attention that when we selecting specified solar modules, we trying to avoid the tolerance and negative value, because negative value will reduce the final productivity of energy from our system. So we must the positive power tolerance. This ensures that we can get or gain more energy in specific environmental condition from the specified module. As we see, it means we can get 5 watt in addition to the nominal rated power of this module. Another type, NTPID, long weather resistance, excellent low light performance, low temperature coefficient. All these criteria must be taken into consideration while we are selecting the base module for our system. Okay. The other important criteria, the temperature coefficient. The temperature coefficient represents a measure of panel's decrease in power output for every 1 Celsius rise over 25 Celsius. Okay, so monocrystalline silicon and polycrystalline silicon temperature range from minus 0.03 to minus 0.5% per each series. For thin film module, close to minus 0.2% per every series, and the thin film represent good option for hotter environmental or the places that experiences more sunlight through the year. As we see this the screenshot of Morpheus module, monocrystalline module, and polycrystalline silicon. If we look at the temperature coefficient data, as we see, for thin film represent the least value, and monocrystalline silicon represent this value, the high value, and the moderate value of temperature coefficient for polycrystalline silicon. So the temperature coefficient for polycrystalline silicon of this type represent less than the temperature coefficient of monocrystalline silicon. It means that the polycrystalline silicon is more suitable for hotter climate for this type, of course, than monocrystalline silicon. Okay. This is the end of the past lecture, and we shall meeting for all in the next lecture. Thank you for your listening, and I hope we will meet you again, and we can say now goodbye. And if this lecture, as you see, good for you, we can subscribe in my YouTube channel, and we can meet in the next lecture, and goodbye for all.